Okay, let's continue. General Chemistry Part 17. Alright, we talk about a reaction in generalized terms and generalized concept about a chemical reaction. Last section, Part 16. Now, we come to the point we have to do something differently from most of the textbook because we are going to learn the chemical reactions. Most cases are in the aqueous solution, which means the reaction will carry out in the water-based solvent. Right? Solvent is a water-based solution. All right. But then we ended with a small discussion we did not completely through, but we finished about a concept confusion between a couple terms. Number one is called the reaction. Well, we talked about the reaction. And then next one is dissociation, which is the term I introduced into this course at this point. And then I said in the very last notes, I said, if you want to judge the chemical process, it's a chemical change process or it's a chemical reaction process, based on if we are able to obtain the products or not, right? We talk about this. And we mentioned there's a process we call dissociation. The dissociation process is a process the solute dissolve first into the solvent, then not only dissolve, like a sugar dissolving water, the sugar molecule used to be crushed into each other as a solid, but then going to the water, it dissolves into individual sugar molecules and submerged in a vast ocean of solvent of water molecules, right? That's a situation we call desolvation or dissolving, right? But then a next step is further down, not only the species or the substance or chemical compound not only can dissolve in solvent, but also can dissociate by itself into cations and anions pairs. That is called dissociation. Now that's a difference. Now we used the table salt last time. We talked about NaCl as a solid. Right? We know that we mentioned so many times, its melting point is so high, 801 degrees Celsius, right? Very high temperature. If you don't know 800 degrees Celsius, I can just tell you the gas stove or the electric stove in your kitchen is only about 475 Fahrenheit, close to 250 Celsius. So 800 is about 3 times higher. So the table salt, sodium chloride, just barely start to getting soft. We call melting, right? But cation and anion in the sodium chloride crystalline structure still stuck together. Alternatively, cation anion in 3 dimension does not separate. Now, but if you drop this ionic compound, sodium chloride, very ionic, right? Very ionic. It is not a covalent bond, right? It's an ionic bond in between each pair of Na and Cl, and there will be quickly, readily, easily dissociate into the water molecule, become sodium cation 1 plus Aq, which is aqueous solution. That's a physical state for sodium cation in the water solution, aqueous solution. As well as the chlorine Cl1 minus Aq in the water solution as well, aqueous solution as well. So they become zillions of pairs of Na and the Cl cations and ion pairs. Now that is called dissociation. They're no longer stuck into a NaCl we call formula units, right? Anymore, because ionic compound we do not have they do not form molecules separated, right? That's what we talk about. So that's a dissociation. So we have dissociation, we have dissolvation, then we have a reaction. Now reaction, if you mix 2 or 3, right, ionic compound, they all to dissolve, dissociate into the aqueous solution, which is water solvent, into zillings of pairs of cation and anion from the original substances, but there's no driving force to make them have any reaction occur. They stay in the vast ocean of water molecule, but they do not form any compound you are able to retrieve as a solid, precipitate down to the bottom of the beaker, or as gas, right, evolved and bubbles out of a solution and separate into, we can collect it, and then we consider them as a reaction product. Or you can form water. If you increase the water amount in the solution, if more water molecules into the aqueous solution after reaction is finished, in that case we call neutralization acid-base reaction. Now those cases are the three driving forces. One is forming solid, one is forming gas, and the last one is forming liquid water. Those are driving forces. And also we have other driving forces to drive the chemical reaction to the completion with something we call products. We can literally obtain from the reaction chamber or reaction beaker into our hand and hold them. That is the criterion we consider that chemical process no longer chemical change, but chemical reaction. You get it? So that is what we talk. So in order to understand this, we need to go back to a little bit back for the beginning of learning about matter. Right? So far we talk about matter, we suddenly jump into reactions. Oh, that's a drastic change. No, we are not doing this. We are gradually build up everything in the same path, or same direction, heading to the one goal or one destination to understand a reaction. So far, we review. It's not the same as, oh, we never learned that. We learned that before. We already talked about solution. We not talk about solution when we talk about solution. We talk about the solution as we are discussing the mixtures, right? The macroscopic matter, including mixtures, and in the mixture category we have a homogeneous mixture and a heterogeneous mixture. So here we are going to talk about what? Reaction aqueous solution. Why are we talking about aqueous? Because lots of many chemical reaction carried out only occurs inside aqueous solution or water-based solution. Alright? And there are another kind of chemical reaction, a big category, the chemical reaction occur inside non-aqueous solution, which is normally the case we call organic solvent. That's a different story. We're not getting there. Right? So in order to understand our major target is the chemical reaction occurred, a lot of them we're going to talk about, in the aqueous solution. We need to understand what's aqueous solution, right? So the aqueous solution, first we talk about solution. So what's solution? Solution says homogeneous mixture in which no boundaries exist between all the components. This is the solvent and the solutes. Now the solutes, why solutes? Because you may have more than one solute, right? And for instance, if you have a table salt, dissolve and dissociate into the water-based solvent, right? And we can talk about what's the definition for solvent and solute. We can just about talk. And then you have two solutes. What two solutes? The cation, sodium cation 1+, aqueous status, right? Because you dissolve in water, dissociate in water, become aqueous as a physical state. As well as chlorine, right? Cl 1- aqueous anions. So you already have two solutes, right? It's two solutes. So that's a plural, not singular. That can withstand the test of time. In other words, if you made a homogeneous mixture, right? There's no boundary. It's not just temporary. Now it doesn't have a boundary, but in the future, you can set that solution on the table for years. It will never separate. You don't see any boundary or borderline between 2 or 3 different components. And that is the key for determining it's a homogeneous or heterogeneous mixture. We already talked about it a long time ago. So solution must be homogeneous mixture with no boundary between the solute and solvent, right? All right. So the example for this, we have 3 kinds at least, right? Now, if you only stopped at the concept about what you learned in the middle school, high school, physical states, we talk solid, liquid, and the gas, right? We did not reach aqueous. But talk about chemistry, general chemistry, we already mentioned so many times, aqueous solution is the most important physical state. One of the four in chemistry: solid, liquid, and gas, and aqueous in chemistry, right? So, but let's go back to the general idea with the three physical states. In the liquid case, we have an example for solution is the liquor. The liquor is made of water and ethanol, 80 proof, 90 proof, 60 proof, Bacardi, right? All these. And then the second one is solid. What is the example for solid solution? The alloys, the coins, the quarters, right? The quarters, and they got copper and nickel in there, right? Copper and nickel in there. And the third kind is gas. The gas we have the most important to our life is the atmosphere, the air we breathe, right? There's oxygen 21% and nitrogen 78% and etc., including hydrogen gas and methane, the carbon dioxide, carbon monoxide, all these moistures in the air, in the atmosphere. They are mixed homogenizely, right? And very, clear. You don't see the boundary between different kind of gas. So those were three examples for homogeneous mixture. We call them solutions, right? Now the solution. Then what is the difference between solvent and solute, right? Solute, right? It's going to be the smaller portions of the solution. So the salt, right, and the aqueous, right, and then you may have an alcohol, right, ethanol, smaller portion, then the water portion in liquor, right, and solute. Then what is the solvent? Now solvent, normally one. Some cases may have two, but solvent most of the time, right, one. And then is the large portion. Right, of the solution. Right. Now in aqueous solution, right? This is in aqueous solution. What is that? Water. Now what is physical state for aqueous solution? H2O, right? We normally, which one you choose? It's got to be what? Liquid, not aqueous. All right, water is liquid. All right, and as we now probably know, a long time ago, water, the pure water is very pure. It's not 100% pure. The pure water does not conduct electricity, and it's a non-electrolyte, and then does not conduct current. But you say, okay, why the water in the flood and people dropping the water and got electrocuted? Now that's not pure water. That's the water that has a lot of debris and a lot of dirt in there, a lot of ions, like cation ions. They carry electrons, and under high voltage, if the power line drop into the flood water and you get close range, it will shock you to death. That's the difference from what we talk about here, water, right? So solvent, solute, right? Then, what is the aqueous solution, right? Cp. All right, aqueous solution is what? A water-based, right, solution with large amount, normally larger than 90% by volume in the solution. All right, so that is so Sometimes you can't even say 99% because you talk about 1 liter of water aqueous solution. There's only a pinch of very little solute dissolved in there, and then the solution already changed color to blue. For instance, you have a cupric sulfate, and there's a blue. It's not anhydride. It's got a little water molecule crystallized into the crystalline structure of the compound. It's a blue color, right? If you drop into water, and then suddenly in 1 liter of water, the concentration is not quite high, it's very low, but already becomes solution because you got two components. One is the water, right? Another one is a little pinch, or a little spoon, or 1 gram or half gram, whatever the amount you need into that 1 liter of water, and the concentration is 0.0 something, very low, but that's no longer a pure liquid as water, or pure solid as solvent, right? Pure liquid as a solvent, and pure solid as solute, and you mix them already, that becomes solution. So that is aqueous solution. Aqueous is a water-based solution with large amount of water, H2O liquid, as solvent. Now this is liquid here, right? But in order to understand the aqueous solution, while we discuss this, there's something we need to talk about. I got 15 minutes, all right. Because in the near future, we're going to talk about one section about the chemical reaction, right? And occurred between ionic compounds, and you have different types of them, double displacement or replacement or single replacement. You involve the solute, and dissociate into cation-anion pair, and right, react with other cation-anion pair, and the driving force drives the reaction to a single direction, irreversible reaction to produce a product. And that product could be solid, or could be gas, or could be liquid. But then you form a salt. This salt is going to stay in the solution until you dry off the solvent, which is water. You cannot get that salt out. Sometimes this kind of salt has the same status as reactants, same species as reactant, as well as the products. Then they are exactly the same in the chemical reaction equation. What is the equation? The equation in mathematical terms means you have equal signs in between two terms or two expressions, correct? But now this time is no longer use equal sign, we use double arrow, right? Either single arrow, one direction, irreversible, or double arrow, two direction, right? Both sides is a reversible reaction, but that considered as an equal sign, and what's called the whole thing we call equation, from reactants to products. But then if the species on the left as part of the reactants is exactly to the other part of the reaction equation as products, they are exactly identical. Now they are mathematically or chemically cancelable. You cancel them as a spectator because they do not really participate in a reaction, right? It's not really involved in reaction, so we are able to cancel it. Then we have the other species left in reaction equation can be considered the real participants of the reaction as reactants and the products, but they are not necessarily in molecular or ionic solid compound form. They become ions, right? So then we are able to understand, if we understand why the aqueous solution here, we introduce something next. It's important to understand that part of the future knowledge we're going to introduce pretty soon, all right? So what happens, all right? Then if you see, okay, then E, right? Dissolution, dissociation, or we call self-ionization, right? Dissociation and reaction. Remember, we left off at this point. Right? We already talked about it before we start this part. We talked about difference, right? So what is desolvation, right? Desolvation. So if you talk about desolvation, let's say I desolvation, right? Solid or liquid and a gas, right? Right? Components, gas components. Dissolves, right? Dissolves into the solvent. But still remain their molecular formula. Without being dissociated into what? Into cation and anion pairs in the solution. Now that is definitely for this desolvation. It is dissolved. The example is what? Sugar into, for instance, this is, for instance, sugar into water. Right, sugar into water. Well, try to leave some space. Now that's different from dissociation. Now what is dissociation? Now, the dissociation process is the substances or the chemical compounds, either 100% or partially or very little, right? Part of their components, part of their total amount will be separated under the influence of a polar molecule in the solvent, which is the aqueous solution right here we talked about. So dissociation, let's put down there, all right? So what is dissociation? Defined as the substance let's put this, the chemical compound right? Most of them, no, let's not put most of them. Compounds, right, are able to dissociate their components let me get this. That is not right. Dissociate. Does dissociate. Can able to separate into the that's the solvent. Solvent in aqueous solution That's water, right? That's water, solvent, to become cation and anion pairs instead of remaining in their ionic compound formula. Under the what? What is the driving force to make this happen? Under the influence of the polar molecular solvent. What is the polar molecular solvent in this case? We talk about aqueous solution, right? H2O. All right, so well, let's talk about dissociation. So the water is a polar molecule. Now we're going to get this in the next section. We got only 2.5 minutes left. So what happens if you have a ionic compound, right? They have where the bonding between the cation and anion, polar bonding, right? Because the electronegativity value is quite big, right? The difference between them is quite big, right? Instead of no 2 is more than 2. So they have very, very strong polarity on the molecule on one end to the other, right? So if they are in a solid form, they all attract each other by their components, cation and anion, they're stuck in the crystalline structure, right? Like a table salt. NaCl, 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 NaCl. So that's alternatively cation and anion, they arrange a crystalline structure, right? But if you drop this ionic compound, which is the ionic compound made of metal and non-metal, right? Sodium is metal, chlorine is non-metal, and it's very strong, and ionic bonding, but they hold it very, very strong. But under the influence of what? Under the influence of water, what is it? The water itself is a polar. It's a polar molecule, but it's not ionic compound. Water is a molecule. But one end is slightly positive, one end is slightly negative. The positive end will be attracting to the negative end of sodium chloride, which is the chlorine ends, and then the sodium end is positive will be attracted to the negative end of an oxygen end. So the water has a force, influence to the ionic compound to split the strongly bonded by ionic bonding, the chemical compound we call sodium chloride. The sodium chloride dropped in the water, the polar molecule as a solvent, is readily, easily breaking down into cation and anion pairs. The sodium Na1 plus aqueous solution status plus chlorine 1 minus aqueous status in the saline solution, which is a aqueous solution. Then that process we call self-dissociation. We already have this equation written on this corner in the part 16. We're going to get that again, and then we talk about the polarity of the water molecule, all right? Based on what we learned from the past on the electronegativity difference to just judge the bonding polarity of the molecule, then the polarity of the molecule of water itself. Then we understand the situation of self-dissociation. That is very important in the future in this chemistry, in general chemistry, in the later part of maybe chemistry 142. All right, and time is almost up, and then a few seconds.